Hi everyone. As I planned, today I will be discussing on the lecture, which is supposed to be in week 8, I think. But for the purpose of your group project, because I believe if we do these topics earlier, it will be very helpful for your group project. Because for your group project later on, you will be using inferential statistics other than descriptive statistics. And also later on, after this topic, the next topic will be on correlation coefficient, which also will be very useful for your group project, right? Because these are some of the statistical tests that you will be using. Okay, so now for in this topic, I'll be covering two main things, which is under the inferential statistics. One is called the student t-test, okay, and the second thing is ANOVA. Okay, so just a recap. So before, oh, so hold on. Oh yeah, what we did in this previous lecture was on descriptive statistics. So you looked at standard deviation, central tendencies like average, median, mean, mode, right? To describe a set of data or distribution of a set of data, right? So now we are going to see inferential statistics. So it's basically is about how we can infer something from a larger population. Usually okay, for example, now when you're doing a survey, you are from a bigger population, you are actually taking some samples and collecting the data, right? So this data will be representing the larger population. So we want to infer something out of this sample to understand the behavior of a larger population, right? So basically you're trying to make a conclusion or find out some pattern or behavior in the sample that can be represented or represented by the population, and whether this observation that you have done in the sample is actually significant enough to for you to claim that yes, this occurs in the population as well. Okay, that is why we have to do inferential statistics. Okay, so the idea of statistical significance, right? Because sampling is imperfect, right? Samples may not ideally match the population. As you know, samples, of course, there are certain ways of identifying what is the best sample size. But sometimes even that, I mean, you can never say that your sample always is perfect, right? So one maybe is the size itself. Maybe it is too small for the actual population, and it was not feasible for you to collect a very large data set, right? So there's imperfection perfection happening there. Okay, other than that, maybe the way you collected your sample itself might be biased, right? You don't know. That is why I always repeat that reliability of your sample is very, very important. The way you collected data is very important to ensure that it is not biased, or there is no favoritism in terms of the way you collected data. Because if those things happen, then what you infer from your sample data may not represent what is actually happening or observed in a population. Okay, all right. So what is statistical significance? So the degree of risk that you are willing to take that you will reject a null hypothesis when it is actually true, right? So it's basically is telling how much, what is the percentage, right, of you rejecting a null hypothesis when actually it was true. So basically this is type 1 error, right? That means your null hypothesis says there is no difference between the mean, okay, but because the way your sample was collected, or the some kind of discrepancies in some data that you collected, right, possibly there is some errors, and it may have caused this error, type error 1 to happen, which is your data, I mean your test actually rejects, okay, the p-value is so small that it rejects the null hypothesis when it is actually true. That means when it's true, that means the mean is not different, right? The mean are equal. But because of the way you have conducted your research, your survey or your analysis, it led you to reject your null hypothesis, and now you have to accept the alternative hypothesis. So usually alternative hypothesis, either it says the mean are equal, I mean sorry, it says the mean is not equal, or if you do one-sided or one tail test, it says the mean is bigger or the mean is smaller than a certain value, right? So this kind of type 1 error can happen. So here you are giving some kind of assurance, like what is the confidence that you have on the results that you are actually getting from your analysis, all right? So for example here, p-value. Okay, what is a p-value that I always repeat during my, from the start of my statistics class? I usually say that we compute the t-value, that also through using the computing tool you can generate the p-value. And this p-value, if less than your critical value or your significant value, for example in this example here it is given 0.05, and that is a normal value that usually commonly used in statistics. If p-value is less than 0.05, it is considered statistically significant, right? So in this case, if p-value is less than 0.05, you can reject the null hypothesis, right? You can reject the null hypothesis and you can accept your alternative hypothesis. So how a test of statistical significance work? Okay, each type of null hypothesis is tested with a particular statistics, right? Like for example, T statistics, right? Each statistic is categorized by a unique distribution of values that are used to evaluate the sample data. We will see an explanation after this, and I also will be sharing some videos which explains p-value from different aspects. Okay, right. So for example, in a typical analysis or survey you're doing now for a group project, first thing what we all ask you to do, come up with your hypothesis, right? You can have many hypotheses. Usually every experiment will be having one hypothesis, right? What you want to test. There's two different relationships you want to test. There will be one hypothesis for that. And then another test you want to do, have another hypothesis for that. So some students or some of you are asking me how many hypotheses we should have. It depends on you, right? How many experiments you want to do, how many analysis you want to do. If you want to do 10-15 analysis, then you have 10-15 hypotheses. Okay, so the first hypothesis, for example, says that mu, okay, basically is the mean. Mu1 equals to mu2. That means the mean from the first factor equals to the mean of the second factor. Okay, so you want to see the relationship. So here you as the researcher or the person who's doing the analysis can determine the significance level. Okay, usually there's another term we use which is confidence level. How confident you want to be with the results, right? That means when you say 95% confidence level, what it means is basically is this. I told you that there is a possibility of rejecting the null hypothesis when it is actually true, right? Which is a type 1 error. So when you say confidence level is 95%, what it basically says that if there's 100 trials, okay, there will be at least 5 times, okay, at least 5 out of the 100 trials will actually reject the null hypothesis when it is actually true. That means there is a chance 5 out of 100 for it to reject the null hypothesis when it is actually true. That means type 1 error to occur. Okay, so if you increase the confidence level now 99%, so there is a chance that at least one time the null hypothesis is rejected when it is actually true. So of course you want the confidence level to be higher and higher, right? I mean, depends, right? As like for example, if in a medical field you want to prove a medicine is working, right? Of course we will go for a confidence level which is much higher. You can even say 99.99% because this is life, right? You are dealing with life. You don't want a medication which was tested using a confidence level of 70%, right? Because if 70%, your p-value should be just less than 0.3, right? If 0.3, you already can reject the null hypothesis and you say that yes, this medication works, right? It is different. The mean is different in terms of effectiveness perhaps, right? But if you choose 99%, then you have to go for 0.01%. I mean 0.01 as a critical value, or also you can call it as alpha value. In that case, for you to reject the null hypothesis, the value of p should be less than 0.01. Okay, so that is not easy unless your data that you collected is large, is very large, and it is convincing enough in terms of the power to reject the null hypothesis. when P is less than 0.01. Okay, so it will be more difficult to reject a null hypothesis as you increase your confidence level. So as mentioned here, if confidence level you set as 95%, then 0.05 is your critical value, or also called as your alpha value. If your confidence level is 99%, then your confidence level is 0.01, or also you can call it as alpha value, right? So this confidence level, the common value used is 0.05, but you can use, or you can try, with the different confidence level for your data, and maybe you will realize that for certain confidence level I can reject the null hypothesis, but when I'm using 95% I cannot reject, but at 80% I can reject. Do some kind of analysis, why does that happen? All right, why at lower confidence level I can reject, when higher confidence level I can't, right? So you should try. Don't just try with one confidence level and you think, okay, oh, cannot reject. Maybe you should try at which percentage you can actually reject, right? Just explore. Okay, so this slide is basically shows you go through when you are doing a t-test, a statistical test. For example, select appropriate test statistics. If you're using student t-test, then the test statistic is called student t-test, right? Compute the test statistic, obtain value, determine value needed to reject the null. That means you have to identify what is your critical value or your alpha value. For example, you choose what is your confidence level. 95% means then your alpha is 0.05. Degree of freedom all based on sample size. Okay, and it depends whether you're dealing with a sample or dealing with a population. Okay, I have shared some videos. Please have a look at those videos for more detailed explanation. Okay, compare values. If p value more than critical value or the alpha value, you accept the null. If the p-value is lesser or equal to critical value, then you reject the null. Okay, so you should know now how you connect your data, because I did explain on how from your survey data, once you key into your SPSS or any tools, that even Excel or any tools that you're using, once you get the p-value, what do you do with the p-value, right? So you must have a alpha value. Your alpha value, you decide what is your confidence level. Then you can decide what's your alpha value. Then from there you can see whether you accept or reject the null hypothesis that you have done. If reject, then you have to accept the alternative. Right? So that is why your hypothesis is important. The more hypothesis you have is the better, because not everything you might be presenting at the end of the group project, but you might pick the things that are interesting and maybe the ones that have some significant findings, right? Okay, so there are two types of sample t-test, student t-test, that I'll explain here. One is one sample t-test. Okay, the second one is two sample. Okay, so basically one sample t-test we use to see whether there is a significant difference between the mean of a population and the mean of the sample that was taken from that particular population. So in this case, you have to know what is the mean of the population, right? So one sample t-test is statistical procedure used to examine the mean difference between the sample and the known value of the population mean. Okay, so in one sample t-test, we know the population mean. We draw a random sample from the population and then compare the sample mean with the population. Okay, and make statistical decision as to whether or not the sample mean is different from the population mean. So here, maybe one sample test here will be useful when you want to check whether your sample gives the same mean as the population mean, right? Okay, there's a second test is the two sample t-test. Okay, two sample t-test is divided into two types. One is paired sample t-test. Another one is independent, right? From the name, you can see that this is about two different samples which are independent. Okay, two independent population means are equal here. So a test helps you compare whether two groups have different average values. For example, whether a man and woman have different average heights. That means in one sample you have all men. For example, if I have this statistic class now, I divide into two groups, men and women. Okay, then I take the average height of the woman and men in this class. So I'm comparing these two sample tests. So here I have two sample. One is the woman and one is the man. Okay, so this is considered two sample tests. But are they paired? No, it is not, right? If I'm looking at men and women, these are independent tests. Paired sample tests are usually something that you are observing, for example, like before and after. Okay, for example, just say this group of students in my class, I am giving a particular lecture on, maybe I get an invited speaker to talk about certain topic, right? So I do a survey first before the talk is given, and then I will look at their understanding on that particular topic of the talk. And then after the talk has completed, I give another survey to test how is their understanding now in relation to that topic. So in this case, looking, maybe if I'm measuring the level of understanding in a particular metric using particular evaluation measures, I can say these are paired because I'm same group of people, students. I'm now testing them, their average, their understanding scores before and after the talk was given, right? So in this case, I can call this sample as a paired sample. Okay. All right, so like just now, the earlier one, the man, woman in a group looking at their height, that is called unpaired sample t-test, or you also can say independent means, right? So used to test null hypothesis when two independent, unrelated groups, in this case, man and woman, or if I'm checking on something year 1 and year 2 students, there are two group of people, all right? So in this case, it is independent. Okay, some assumptions about t-test. Usually it's normally distributed. Okay, some students from previous classes also what they used to do when they are doing, they are checking their data, because there's so many assumptions here, right? When you're using parametric tools, statistical tools, it has to be random and it has to be normally distributed. So there is a way of checking whether it's normally distributed. You can actually plot an histogram or bar graph to see whether you get the bell shape or not. But sometimes you don't, most of the time you won't really get a bell shape because unless your data is very large, maybe you will get a bell shape data, okay, distribution. But it's okay, you can still continue using parametric tests, right? Because we understand at this I mean, within this one few months, you might not be able to get a very large data set that produces how to say, a bell-shaped curve, right? So it's okay, you can try with parametric tests, but nothing wrong for you to even try with non-parametric tests as well, because non-parametric tests is quite lenient in terms of that, not that strict, right? It does not assume a normal distribution and things like that. Okay, it is lot of things that you don't know about the data. There is a flexibility when you use non-parametric tests. So why don't you try with two different tests? Okay, sample is large enough. Actually, usually for if you see some of the slides or some books or even some YouTubes, they talk about when you use student t-test, the sample size should be less than 30. Okay, but please understand that even if you are having a sample size which is more than 30, there are studies showing that t-test can still be used, and there is not much of a difference in terms of like, it's not a hard rule that you mustn't use t-test if it is more than 30, because when it's more than 30, automatically the way the method used in statistics will follow the z-test. Okay, because if more than 30, you normally use z-test. Okay, you don't use t-test. So but it's okay, you can still use t-test, but it eventually it behaves like a z-test, right? So if you want to try z-test as well, you can, but go and have a look at the assumptions as well before you use the z-test. Okay, so one example here. For example, just say a null hypothesis says there is no difference between the means of the group y1 and y2. Okay, maybe I skip just now. What is y1, y2? Assume that a study has been conducted whereby 5 students were randomly selected from year 1 and year 2 each, and their blood pressure were measured. So 5 students in each group, okay, different group of people. So you want to see there's no difference between the mean of the group from y1 and y2. So null hypothesis, as I told you, usually is the understanding is there is no difference. Okay, so the mean is equal. The alternative hypothesis, in this case, we are using there's a difference between the means of the group from y1 and y2. Okay, so this is two tail, which is mean y1 not equals to mean y2. So can you see, Anna, from this alternative, if you do this test, okay, a two tail t-test here, you will know that they are not equal. But will you know which is bigger or which is smaller? No, you don't, right? If you want to know which mean is bigger or which mean is smaller, then you use a one tail t-test. Okay, One tail will be your mean, your alternative mean will be, for example, you will say, hold on, yeah. So perhaps you can say, okay, mean y1 bigger or equals to mean y2, okay, or mean y1 smaller or equals to mean y2, okay. Sorry about the line there, okay. So this is, these two, okay, it is one tail. Sorry, I'm not sure why that line is coming. This is one tail, okay. When you have bigger and smaller, okay, if you do one tail test, then if your null hypothesis is rejected, then you know which mean is bigger or smaller depending on the test, right? So you have to be careful when you're using one tail, which are the when you are inputting the data, you must see which one to enter first, y1 data or y2 data, because you want to see which is bigger than which factor, right? Okay. So in this case, t-test, assume that when t-test is done, the p-value obtained is 0.03. So if my confidence level is 95%, my alpha value will be 0.05, correct? My alpha value will be 0.05. So if alpha value is 0.05, so my p-value here now is 0.03. So p-value now is less than 0.05. So my how I infer this results is, we reject the null hypothesis and conclude that there is a difference between the mean of group from y1 and y2. Okay, that's how you infer, right? So just say I choose my confidence level as 99%. Do I get the same results? Okay, if I put 99%, my alpha value now is 0.01. Okay, so now if your p is, not sure why is this happening. All right, if p equals to 0.03, this is smaller than, sorry, this is, just hold on, yeah. So if 0.01, okay, 0.03 is bigger than 0.01. Okay, so when 0.03 is bigger than 0.01, I cannot, right? I cannot reject the null hypothesis. I cannot reject null. Okay, I cannot reject null because 0.03 is bigger than 0.01, right? So in this case, the conclusion is different. This is what I told you, that as you increase your confidence level, your alpha value becomes smaller. It is much more difficult for you to reject the null hypothesis. So it all depends on the needs of your study, right? How critical is it to increase the confidence level? Okay, if it's not critical, then it can be lower than 95% also, right? Okay, so try with different confidence level for your studies, for your analysis of your project. Okay, so here's another example. Teacher satisfaction in public and private schools. So there was a survey done to see how satisfied are teachers who are working in public and private sector. So as you can see, the first column is the public sector. The mean was 6. And private, the mean was 9. Okay, this in terms of satisfaction, right? Some values. Possible they used the scale, right? The scale of agree, disagree, and things like that. So those values are put in here. So by looking at the means, we can conclude that private teachers are more satisfied than public. But is this really significant? That is why in statistics, we sometimes don't accept this kind of results unless they are proved significantly they are different or not. Because this may be just by chance, right? So that is why you need significance testing here. In this case, you're using t-test. Okay. So after we use the SPSS, we keyed in the data. So we saw this, so hold on. Okay, So SPSS produced this result. So in SPSS, when you use t-test, this is where you see for the p-value. So if you can see the p-value when equal variance are assumed, usually equal variance are assumed, right, in your study, unlike it's not that situation, then here the result is 0.017. This is a p-value, okay, it's a two-tailed test, 0.1017. So p-value here 0.017 is less than 0.05 alpha value. So satisfaction between the groups was significantly different. Then you can see yes, it is not by chance, but there is a significant difference in terms of satisfaction of the teachers in private and public school, right? Okay. So there are some examples of videos that I have shared here. Please go through each of them, right? There are some of a good examples. Some examples I also shared that relates to how to use in SPSS. Okay, but these are more to not SPSS but on explanation. Okay, if those who are not using SPSS, there are also a lot of videos on how you can use Excel. But please mind that Excel have some limitations. For example, when it comes to ANOVA, you can even do ANOVA test in Excel, but when it comes to post-hoc test, you might not be able to do. Okay, yeah. So if you can install the trial version of SPSS, that will be good just for the practice purpose, right, or to understand further. All right, for ANOVA. Okay, so next, what is ANOVA, right? So just simple, right? You use ANOVA when you have more than two means to compare, right? So all right, so in real life things do not typically result in two groups, right? Usually you might have more than two groups. Okay, if you're only looking at male female, okay, maybe there's two groups, but sometimes you have more than two things that you want to compare, right? Okay, here let us see. Two sample t-tests are problematic. Okay, of course, increasing the risk of type 1 error, as mentioned just now, right? The type 1 error where you reject the null hypothesis when it was actually true. Okay, and then at 0.05 level of significance with 100 comparison, 5 will show a difference when none exists, right? So the more t-tests you run, the greater the risk of type 1 error, rejecting the null when there is no difference, right? Okay, so one other ways you can do is when you have more than two different um, groups, okay, you can use ANOVA. Okay, so let me skip this one. Okay, I'll go to the more important things. All right. Okay, so variance between or within groups. Variance can be separated into two major components, right? One is within the group or between the groups. Okay, for example, just say gender. Okay, no, maybe not gender. Okay, just say marital status. Okay, married, not married, partner. That means maybe you're already partnered or you have engaged, right? So these are different levels of marital status. Married, not married, engaged, partner, or something like that. There are more than two, right? So um, within the group, that means when I say within the group, that means in the group of marital status factor. The marital status here is a factor, right? So is there to see any difference in terms of the mean, significant difference within this particular group? You can use ANOVA. Okay, another thing is to see between groups, right? Between different groups, that means maybe marital status is one, and then another for example, different depending what group one is in or what treatment it received, right? So between this group of data with another group, right? So it can be between two different factors. Okay, maybe marital status and maybe the, for example, effectiveness of something, right? Two different factors. Okay, so we will see through example, maybe that would be much easier. Okay, let's see factors that have two or more levels. Okay, male or female is a common thing. Gender, we have two levels, right? T-test can be used to compare this, right? Because there are two levels. So other than this, maybe any other things that you have two choices of answers in your survey, you can use normal student t-test. Okay, for example, just say like what I said just now, marital status may have four or more. So for example, single, partnered, married, engaged, and others. You can use ANOVA. Okay, so statistical test for one-way design can be parametric or non-parametric. Okay, just highlighting here, although parametric you can actually cover in the last chapter, but I'm just letting you now know now, if parametric, that means if you have your data has fulfilled certain things, right? Like it's random, independent values, it is normally distributed, right? So you can use parametric test. Okay, so it's independent group t-test. Then for 2 levels you use t-test. But if more than 2 levels, 2 plus 1, that means 3 and above, you can use ANOVA. Okay, you might ask what is one way ANOVA and two-way ANOVA. We will see after this. Okay, one way basically, okay, I will show you after this what is the difference. Okay, if the same thing now, if you want to use non-parametric test, because of the assumption of the data characteristics of the data, for student t-test, instead of student t-test, you can use Mann-Whitney. Okay, you can use Mann-Whitney test is equivalent to a t-test, but in an environment of non-parametric test. Okay, in terms of ANOVA, ANOVA is used for 2 plus 1 in parametric test. Instead of that, you can replace with Kruskal values, which is also used for 2 plus 1 levels. I mean more than 2 means. You can use Kruskal values under the non-parametric test. Okay, if I were you, I will try all this for my data that I have, right? Just to see how the data, I mean, how is the outcome when you use parametric test and when you use non-parametric test. So for example, just assume difference between two means use t-test, right? So this is how you write null hypothesis. There's no difference in the mean, okay? The mu1 equals to mu2. So the null hypothesis is false if mu1 not equals to mu2, right? This is two-tailed test. So the alternative hypothesis, there is a difference between the means, okay? So this is for the typical t-test. But how is it in one-way ANOVA, right? So differences among two plus means, that means more than two means. Mu1 equals to mu2 equals to mu3. Okay, that means there is no difference among the mean. The null hypothesis is false, okay, for alternative. Alternative hypothesis says that there is at least one difference among mean. So you please understand that in this alternative, you don't know which one is different, correct? In one way ANOVA, you only can say one of it is not equal. Because one of it, just say u1 not equal to u2 or u2 not equal to u3. One of it is not equal, it will reject the null hypothesis. Okay, but at this point you won't know which is not equal. Okay, that is what he's trying to say. There is at least one different among mean which you don't know which one. Okay, right. So some of the assumptions as mentioned just now are independence of observation, normality, and homogeneity of population variance. Okay, right. There are some videos that I shared which is very important. I would really suggest you to go through all these videos. They're short videos but they are quite useful, right? You can look at t-test for two different means. This one is understanding hypothesis and also linking it to the p-value, t-test, and how the difference of two means. Okay, have a look. And also you can look and try to understand what is p-value. Okay, and I also shared here one link to two means t-test using Excel. Okay, and then if you go to that particular uh, videos, groups of videos, you can see some links to different ways of doing this test using Excel. Okay, if you want to use. So some of the basics of ANOVA that you need to know. It wants to study the effect of one or more qualitative variable on a quantitative outcome variable. Okay. So qualitative variable here can be any kind of factors. For example, marital status or education background or which batch they are from, you know. So these are all qualitative variables. Okay. But you are going to measure them, how effective are they based on the significance value. That is why you look at ANOVA value. So characteristics that differentiates factors are referred to as levels. So for example, the characteristics for marital status, there are 3 levels, which is married, single, and partnered. Or maybe you have 4 levels, married, single, partnered, and engaged, or something like that. Okay. So for an example of ANOVA here, they are assume there are 25 patients with blisters. Okay. Treatment A, treatment B, and placebo P was given. So measurement equals to number of days until the blister heal. So the numbers that you can see here is basically the number of days taken by the patient to heal their blister. So A is treatment A, B is treatment B, P is placebo, right? So are there significant difference? So first thing, you must understand the size here also is different, right? I think this has about 9, and this has about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Let me see. 4, 5, 6, 7, 8. No, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8. Is it 8? Okay. 8 here. 8 here, 16, and this one got 9. So 25 patients altogether. So if you can see, this is the mean for each of the group. So there are 3 groups here, 3 means here. Okay. Are they significantly different? Based on the magnitude, if you see, yes, you will say it is different, right? So, but you can use ANOVA in this case to see whether they are significantly different. So at the simplest, there are extensions on our test the following hypothesis. For example, the means of all the groups are equal. Okay. The alternative will be not all the means are equal. But it doesn't say which one is differs. Okay. It doesn't say which mean is different. It just says that they are not equal. Okay. So if you want to know which one is actually causing the difference, you can do a follow-up test which is multiple comparison. Okay, something that's called Tukey, right? That you also will try later on in your tutorial. You can do a Tukey test, or if you see some of the videos that I gave, you also can see. Once you know, yes, they are significantly different. Now you want to know which one is actually causing the significant difference. You can use a Tukey, right? Tukey. All right. We usually refer to the subpopulation as groups here, or you also can say as, yeah, you can say subgroup, or you can also say subpopulation or groups. Okay. All right. These are the normal assumptions. Okay. So some of the assumptions here that you have to follow is standard deviation of each group are approximately equal. So the rule of thumb, ratio of largest to smallest sample standard deviation must be less than 2 to 1. Okay, which I will show you in the next example. Okay. Okay, you also can do a normality check, okay, by plotting a histogram, okay, and to see whether the data is in a bell shape or not, or is it yeah, in a normal shape or not. For example, this is the standard deviation check. Okay, it can be done in SPSS as well. So here just I'm trying to show the three different groups and the standard deviation. Okay, so the largest here is 1.764, the smallest is 1458. So if I double, the smallest is 2.916. Okay, so it's basically, it is much smaller than 2 to 1 ratio. Okay, so you can do this ANOVA, right? Okay, so some of the notations here, okay, which I won't go through these notations. We can, I think this is self-explanatory, right? Okay, so I will show you once you do the ANOVA in your SPSS and or any other tools that you get, okay, that you have installed. Like this is from SPSS, this is from R, right? ANOVA output. Let me see. So you can see this is degree of freedom. Okay, degree of freedom. So there are 3 treatments, right? So the degree of freedom here is 2, right? And then this is the F value. Okay, F value is used to generate the P value. But in your case, you don't really have to, because for example, in student t-test, right? The statistic T, T statistic value is used, right? Can be used to refer to the T table to see whether it is significant or not, right? Here there is F statistics when you ANOVA, but when you are generating using a computing tool, you can always use the P value to see whether this P value is lesser than the critical value or not. If this like in this case is quite small, right? If say for example, if it's 95% confidence level, your alpha value is 0.05. So 0.006 is smaller than 0.05. All right. So in this case, it is significant, right? The difference between the mean, the mean between these 3 different groups is significant. Okay. So I've shared some videos here on ANOVA. Please go through, right, to see what is a two-way ANOVA, one-way ANOVA versus two-way ANOVA. Okay. Yeah, and then some which is relevant to SPSS as well. Okay, here I did not mention on the two-way ANOVA, but you can actually see the video that I given here on what is a two-way ANOVA, and then I will also explain on Tukey and how do you do multiple comparison once you already done the find the significance using ANOVA. All right. So this we will do in the next tutorial for this particular topic that we will upload earlier, so that you can try earlier and we can discuss earlier, so that you can start doing and apply it in your group project. Okay, so maybe during our next meeting, if you have any questions, you can always relate it to your group project and you can ask and we can discuss then. Okay, I think that's all for this, right? Which is we have basically covered something that relates to your So the next lecture I will be doing on correlation coefficient, for example, Candle-Stowe, Pearson, Spearman, right? So this also you need to apply in your group project. The best thing is all the different statistics tools or tests that we are explaining to you, please try. Even the non-parametric, it's okay. You can try both, right? You can always explain that why, okay, the assumption of this data is normal, independent, so you're using parametric, fine, right? But no harm trying with non-parametric, just for you to explore and see how do they differ, how the results look like if I use different tests. Okay, right? So please don't forget, put the assumptions of your data as well, right? Most probably it will be non-parametrics, because you might not get a normal distribution. Okay, so that is why I don't want you to restrict yourself from not using parametrics. Okay, please explore parametrics as well. Okay, all right, thanks. Yeah, we will keep you all updated through our tutorial groups. Okay, thank you.